Hey there, welcome to another math video. Today we're gonna solve a problem from the Cono Sur Olympiad 2016, problem 6. And the problem is exactly as follows. So we call a triplet of positive integers ABC friendly if one of them divides the product of the other two, like here. And we are supposing that they are pairwise distinct. And okay, what we are trying to look in this problem is whether it's possible to have, like in these types of intervals right here, triplets or friendly numbers. And in the first one, if we have like a perfect square and we just take a very small interval after it, we'll show that that is not possible. And then after it, we increase a bit more this interval. And we are asked again whether we can find such a triplet. Okay, so let's go for the solution. We'll start with part A. So for part A, if the thing is true, then exists, so by contradiction, there would exist ABC pairwise distinct ABC belonging to 1 up to n-1, such that, well, we know what must happen. N squared plus A divides N squared plus B times N squared plus C. Okay, so yeah, we want to know whether this is possible. And okay, what we like to do when there's this kind of stuff is to reduce like the order of the thing that is divided. So we know that n squared plus a divides n to the 4th plus n squared times a, and it also divides n 4th plus n squared b plus c plus bc. So it also has to divide the difference, which is n squared b plus c minus a plus bc, right? But it also divides b plus c minus a, b plus c minus a, n squared plus a. So it divides the difference again, right? So this part will cancel, divides then a, b plus c minus a minus bc, which is ab plus ac minus a squared minus bc. And we can factor out some stuff here. So this is ab minus a minus c minus a, which is a minus c, b minus a. So n squared plus a has to divide this thing, right? N squared plus a has to divide this thing, great. But what's the problem? Well, the problem is that then the absolute value of n squared plus a has to be at most the absolute value of a minus c times the absolute value of b minus a, which is less than n plus 1, n minus 1 squared, but then this is n squared plus a, which is greater than n squared, so absurd. Okay, so this proves part A, that this is not possible, this thing here. Now let's move to part B. What else? What can we do better? Okay, now we have a bit more tolerance, but so we still observe that this thing has to hold true, so n squared plus a divides a minus c b minus a. This is an important point, right? Okay, what's the thing? We will try to construct an example, and the idea is to, well, we want to construct something, let's say n squared plus something in the format of n squared plus a equals, let's say, b minus a, c minus a. This would solve our problem really well, right? If we can do something like that. So the idea is to try to find an a which is relatively small, such that this n squared plus a factors out as something nice, as like two relatively small factors as well, so that we can call one of them b minus a and the other one c minus a. So what we basically want to do is to have basically like a, b, c, let's say something like this. So, and hopefully n will be much further away here. So what we want is to have those numbers small. Okay. So one interesting factorization is n plus k plus 1 times n minus k. This will equal n squared plus n minus k times k plus 1. Okay, I'll just give an example. So if we have like n equal 13, we can get like the largest k that we can get. We take k equals 3, then we will have 17 times 10 equals 169 plus 13 minus 3 times 4. Okay, so we get to something great, because we then just take a equals to this n minus k plus 1, which is just 1, b equals a plus n plus k plus 1, which is 18, and c equals a plus n minus k, which is 11, and everything is in our interval. Okay, because we can 13 plus 3 square root of 13, and this is smaller than 3 times 9, oh, 3 times 3 times 13, which is 22. So we are fine. So okay, we have that example, we have the idea. What we want to do is to take this the largest k that we can. So choose k such that k plus 1 is smaller than n, which is smaller or equal to k plus 1 times k plus 2. Okay. So what do we want? We basically want the the numbers to be well on our interval. So what will be the trickiest one? To be B, right? It's the largest that we have. This is how we define ABC. This is how we are defining them, and we are defining K like this. Okay. From these definitions, then B is the largest. And then we want n minus k plus 1, which is a plus n plus k plus 1. This has to be smaller than n plus 3 square root of n. This is equivalent. I'll just put here a question mark because it's what we want to prove. Okay, so what we want is minus k squared plus n plus 1 smaller than 3 square root of n. Which is entirely equivalent to n minus 3 square root of n plus 1 smaller than k squared. But then we use this bound here, n minus 3 square root of n plus 1 is smaller than what we get when we replace this. And then this we'll try to prove that it's smaller than k squared. And here we'll come back. Okay. This we want to prove that it's smaller than k squared. This is equivalent to 3k plus 3 smaller than 3 square root of k plus 1 k plus 2, which is true. Right, we just go back to this smaller point here. So if we define f of x as x minus 3 square root of x plus 1, then f prime of x is 1 minus 3 over 2 square root of x, which is positive if x is bigger than 2. Okay, so the function will be increasing, so we will be fine with this bound here. We just have to check up to n equals 2. Okay. Okay, but except for this small case, we are done, right? Because here we just proved that the condition that we wanted holds. That is, that all of the numbers a, b, and c are smaller than n plus 3 square root of n. They are also supposed to be all different. Yes, they will be all different because well, we have a, which is strictly positive by the definition of k. Then we have c, which has to be bigger than a because n minus k is positive, and then we have b, which has to be bigger than c, so they're all distinct 2 by 2, so we are fine with respect to that. The last point then is just to check up to n equals 2, and then here we'll just play it around. Okay, so n equals 1. We are looking then in the interval 1, 5. we don't have too many triplets there. And none of them, and it doesn't work. And then equals 2. We'll have the interval 2. We'll have the interval 4. Then 6 plus 3 times 1.4, which is 10.2, let's say. And here it should be easy to find, because we have, for instance, we have 5 divided 6 times 10, which works. So except for n equal 1, we will be fine, and we will be able to find such a triple. Okay, so thank you very much for your attention to this video, and see you in the next one.